Dear colleagues, hello. So I'm happy to give a talk on a fourth spectroscopy winter school, and today we will talk about confocal Raman microscopy, principles and its applications. What is Raman spectroscopy? It is inelastic scattering when the excitation photon interacts with the material, with the structure, and there is a probability that emitted photon have different energy, and the difference corresponds to energy level density, energy level populations, and therefore if we measure shifted photons, which could be shifted both in stocks, in lower energies, or in anti-stocks in higher energies. So if we measure spectroscopy of these photons, we will find very sharp peaks which are different for different structures, and this is kind of fingerprints of materials, and by making this spectroscopy we can identify chemical structure and some physical parameters. So, but what is the main problem? The problem is that the intensity of such characteristic scattered light is very low. It is very weak signal, and to collect such signal we should use high sensitive detectors, and also we should suppress the excitation wavelengths, excitation laser intensity, because normally Raman scattering is about 10 to the minus 7 in respect to excitation intensity. And it's also very important to choose a proper wavelength to excite the sample. Here you can see example of same material, polystyrene and PET, and this material has different efficiency when excited by blue laser, by green and by red laser, and especially infrared. So the issue is that the shorter wavelength of the laser, the higher cross-section of the Raman signal, the higher efficiency of excitation of Raman signal, and it is proportional to the fourth order of the excitation wavelength. Another thing, the Raman signal quite often can be overlapped by fluorescence, and to avoid such overlapping, such masking of the Raman signal, we should choose either wavelengths of excitation in the red region or in UV region. Okay. So how can we get high spatial XY resolution? We should use confocal configuration. The main principle is that the sample image is projected to the pinhole, which is a square shape pinhole, variable size, and as a result the signal from volume of the sample, not from the surface, it comes to the pinhole as defocused spot, and only signal from the sample surface, where the objective is focused, it goes to the pinhole without disturbance, and after the pinhole it can go to the detector. And same for XY resolution. If the signal comes from a side, then it is blocked by pinhole, and therefore we can achieve a high resolution which is limited by diffraction limit. This is the typical diffraction limit for optical microscopy. It is about 0.6 times wavelength lambda divided by numerical aperture of objective, and about Z resolution it's more complicated ratio, and more or less we can say that it is twice bigger than lateral resolution for the selected numerical aperture, the selected configuration. And here we have image of two main models. So we can see on the left hand side there is upright configuration when the light comes to the sample from the top, and on the right hand side there is inverted configuration. Both are combined with confocal Raman spectrometer. Okay, and let me show you how it works inside. So you can see there is excitation laser which goes through some beam combiner which combines light from different excitation lasers, and then light goes inside the main unit. What are the main parts in this unit? So first of all, it is neutral density filter to change intensity of the light which goes in the sample onto the sample. Then there is an analyzer or cleaning polarization. Usually it's a Glenn-Taylor prism. Also there is a beam expander which make a beam perfectly collimated, and also it make it a desirable size, which is very important when you switch between different objectives. The size of the beam should fit perfectly to the size of the input aperture of the objective, which is different for different objectives. Okay, so we have a collimated beam of desired size, desired diameter. Then we can use, by lambda half plate, we can rotate a polarization of the light. Here there is a module for changes between different edge filters or notch filters. So when one change excitation wavelengths, the filters should reject laser intensity, and they normally are highly transparent for higher wavelengths. Okay, so light then go to the scanning system, and then it is coming to the XY to objective, and sample is mounted onto the XY stage. Okay, then the light which interacts with the sample, it has, in addition to excitation wavelengths, it has a Raman signal, Raman scattered light, and these photons which are shifted by wavelengths, they go through the edge filters, can be analyzed by polarizer in detection channel. Also there could be a band pass filter, and this is pinhole objective which focus the light onto the variable size pinhole, and the same position is here. So light, after the focusing to the pinhole, it goes into the spectrometer. So we have reflective optics inside. There is a parabolic mirror which make a beam collimated and then send it to the grating. They are automatically switchable, and these gratings, they make a linear angular dispersion of different wavelengths and focusing, and then the mirror is focusing light onto the CCD detector, or if we need fast mapping, we can send light through the slit to point detector like PMT or APD, avalanche photodiode. And also the reflected light partially goes to the separate confocal scheme just for relay scattered light detection. So in addition to Raman signal, we can collect the PMT. By PMT we can collect intensity of the laser signal, just intensity of the laser. Okay. So this configuration consists of some important parts. First of all, it's true confocal design, which allows to vary pinhole size to perfectly fit to the magnification of objectives and numerical aperture of objective. And therefore, diffraction limit of resolution can be achieved, for example, 200 nanometers with blue laser and immersion optics. It means oil immersion objective on the microscope. Thanks to high quality coatings, we can achieve about 70 to 80% of throughput of the spectrometer from input pinhole to CCD position, and therefore it gives total about 50% sample to detector throughput. And we can change easily by software up to 5 lasers, which are automatically changed by filters, motorized filters, and shutters in the entrance unit. Also, gratings, polarizations, and beam expander, they are also fully motorized. And the system can be equipped by several detectors. It can be CCD with front or back illumination. Also, it can be fast EM, electron multiplied CCD, or deep depletion CCD, or sometimes you need cover visible range plus infrared range, and in this case it is possible to combine two CCD in a single spectrometer and switch between them by this rotatable mirror. And up to 3 detectors can be used in spectrometer channels. And this is a fully automated confocal Raman microscope, the model called Ramas N500. And for the high quality optics, we can use, depend on the needs, we can use metal coatings, for example, aluminium with protective magnesium phtor 2 coatings, or for visible range and for near infrared range can be used silver mirrors or silver coated gratings, and also for infrared region gold coated gratings and mirrors are recommended to use. So you can see gratings can be optimized for defined wavelengths, and therefore the spectrometer provides best sensitivity in the desired spectral range. And of course we can use interference optics, which is good for the wavelengths in the visible range. And here you can see layout of another system, another instrument. It's less automated. It has several lasers, up to 2 lasers can be built in, or more lasers can be used with external beam laser combiner unit. And inside there is automated shutters to open and close lasers. Also there is a automated neutral density filter and switching between edge filters. And what is not automated in this configuration is beam expander, which probably not so often should be changed if you use a system with a single laser. And also positioning of the mirror which sends the light to the pinhole, it's also manual in this configuration. And the spectrometer, all the gratings, all the motors for the mirrors, they are automated. And what is also important in this configuration, the laser is built in mainly, and also the coupling between confocal unit and spectrometer unit, it can be done by optical fiber. So for this configuration it's not important to put everything on the optical table, so it's more flexible system. Okay, there is another overview. So it can be combined with the spectrometers of different focal distances, and it can be varied from 200 millimeters up to 750 millimeters for high spectral resolution. So resolution is proportional, directly proportional to the focal distance, focal length of the spectrometer. And also there is a special option for 1 picometer resolution, which is used so-called Boolean add-on unit. So all of these systems, they have high reproducibility and a high accuracy mechanism, motorized mechanism, and also built in wavelength calibration procedure. And for best performance, it has for best wavelengths, it has efficiency up to 78% from input to output. And as I said, it can be equipped with different number of detectors. And here is another system. It is E200. It is a compact designed system when the unit, spectrometer unit and confocal unit, they both combined together with optical microscope, and they are mounted on top of the microscope. So this gives additional, so it's a compact design, but nevertheless the spectral resolution can be less than 1 wave number. And this is a system with 2 lasers. Up to 2 lasers can be used. This is the most affordable system. It has no movable parts, so we remove all the units which are not so important for most of the Raman applications, for most of the Raman samples measurements, and but still we have all options which are mainly used. For example, automated laser attenuation control. Also there is a possibility to choose notch filters instead of edge filters, and therefore to get stocks, anti-stocks measurements, and even low wave numbers measurements are available here. Motorized stage, also remote fiber probe option. All these options are available with system S120. And this is the parameter, so it provides a resolution about 4 wave numbers with excitation laser 532. And there is a typical spectrum obtained with such a compact designed system, and the spectral width at about 700 nanometers. It's only about 0.2 nanometers, and therefore full width at half maximum at true spectral resolution is about 4 wave numbers. And of course, such a spectrometer unit can be used also without microscope. So in this case, we can get model for tabletop Raman spectroscopy. It can be used as a direct spectrometer, direct light focusing, or fiber probe light. And again, it can be equipped with both blue and green laser, for example, and provide resolution down to several wave numbers, which is usually enough for most of applications. Okay, and this is typical window of software for operation for Raman and fluorescence, and has automatic fluorescence background subtraction. Also such mathematical operations like stitching of spectra, peak fittings, cosmic ray removal, and so on. All of them are available in this software. Also on the left hand side you can see the neon lamp spectrum, and there is a built-in neon lamp inside spectrometer, and software can perform such calibration procedure. So now let's take a look what are the applications of such systems. First of all, normally what is the basic application is you need to find some structure on the surface, and from this selected point then we should take a Raman spectrum. So you can see there is a viewing microscope image, and there are molybdenum disulfide structures on the surface, on the silicon surface, and here we can see spectrum for selected structure. And this is example of high spatial resolution, XY resolution. Sample is a mineral spheres, and they provide strong Raman signal. And when we use oil immersion objective with 10x with blue laser, excitation blue laser, then we can achieve about 200 nanometers resolution. And another important parameter of the Raman microscope is sensitivity. So silicon is a quite common standard to check sensitivity of the system, and here with the standard parameter of a pinhole, laser excitation laser was 473 nanometers and with the power about 11 milliwatts. Air objective, not oil immersion, just air objective was used, and fourth order of silicon can be detected just by 150 seconds easily, and fourth order of silicon is clearly resolved in this case. And to get better signal to noise ratio, 600 seconds can be exposure time can be used, and then it shows really good signal to noise ratio. And the same CCD camera, when we switch to EMCCD mode, it can give Raman spectrum with a reasonable signal to noise ratio just for about 2 milliseconds, and this integration time is enough for mapping, for acquisition of single point spectrum, and therefore this camera is quite good for high speed mapping. So one of very important application of Raman spectroscopy is identifying structure of carbon nanotubes, and there is so-called radial breathing mode band, which is located around 150, about below 200 wave numbers, and this intensity of these peaks and position of the peak, they are directly connected to the diameter of nanotubes. So this is equation, and the ratio is the following. So by measuring Raman spectroscopy and finding position of the single wall nanotube, for example, we can identify the diameter with very high precision. Here is the image of carbon nanotube obtained by objective with 0.95 numerical aperture, and this image is obtained by XY motorized scanning stage. So the position is good enough to get about 100 nanometer step size, and the overall image is about 1.5 times 1.5 microns, and intensity is intensity of the G band, so a brighter color, a higher intensity of this selected band on the point, on the surface. So we can take a look on the graphene typical spectrum, and by when there are different number of layers, energy state in the graphene structure is changing, and single layer graphene has a clear difference compared to two-layer graphene, and three or more number of layers, they are not so so clearly differentiated by 2D band shape, and one or two layers can be clearly identified. And this is example of such map when one layer and two layer graphene, they were identified by point Raman mapping, and therefore we can tell which position corresponds to required number of layers. And another application here you can see is identifying a temperature of the structures on the surface. So in this case we know that population of energy levels, it is defined by temperature of the structure, and the higher the temperature, the more equal population on higher levels and lower levels, energy levels. So it means if we collect Raman spectroscopy for both stocks and anti-stocks, we can find the ratio of these peaks, and from the ratio there is a possibility to calculate temperature of the sample. And for this suspended graphene, which was used, and in this experiment there were a current applied and the voltage applied to such structure, and in the central region the temperature was about 1700 degrees, and on the substrate, when the graphene were laying on the substrate, temperature was about 800 kelvins. Okay. Another application, by what other information can we get from Raman spectroscopy? So temperature, it was possible to get, but what are other information, what are other parameters? And one of important parameter is internal stress, and such stress can be measured for example for diamonds, and on the borders of crystallines on the surface, microcrystallines, there is a changes in the stress, and this the line of the diamond 1332, it is shifted slightly and also a little broadened because there are some defects on the edges of microcrystalline. And when we make mapping of the selected band, we can get information about stress in the sample, in the structure. Another information is domain structures. For example, this is ferromagnetic material, lithium niobate, and Raman bands slightly changes when you collect it in the center of the domain region and on the domain walls. So black color is domain walls, and you can see on the bottom spectrum, on the bottom image, there are two spectra, black and red color, and there are slightly small difference. So left peak is higher, it has a higher intensity for domain walls, and the right peak vice versa, it has lower intensity for domain walls. And also there is a small shoulder. So if we choose such a peak at 570, 580, and we make a mapping of intensity of the peak, so we will get brighter regions which corresponds to domain walls, domain borders. Another example is identifying materials. So we can get information about what type of polymer is in the on the surface. And because here we use a polymer blend of polystyrene and polyvinyl acetate, and they have a quite different Raman spectra. So the top one is for polystyrene and the bottom one is a polyvinyl acetate. And intensity for selected peaks, so first peak for polystyrene, about 1000 wave numbers, it's on the right hand side, and the other one is for polyvinyl acetate, it's about 3000 wave numbers. So we can see that the matrix is clearly made of polystyrene, and on the surface in the matrix we can see some domains of polyvinyl acetate. So another, for pharmaceutical needs, it's important to know how well different components are mixed inside the tablet. And there are two components. First is aspirin and the other one is paracetamol. And red color and green color, they show the pure material, and yellow color, it's kind of both spectra are collected from this region. So by mapping of the tablet we can see that both components are in a pretty good mixture between each other. And when we need to make a large map, and for example when we need to scan by piezo normally XY piezo stage, normally it has a limited scanning range, so then we can do some stitching and collect several scans and stitch them together. So, and therefore to get a high resolution image for the large area. So this is possible when we use XY scanning stage. And when we use XYZ scanning stage, we can do XZ profiling. It's important when we need to know structure of the sample in Z direction, some depth profile. And in this example we can see silicon coating of about 2 micron width, 2 micron thickness on the top, because the peak, Raman peak, at about 2900 wave numbers, it's clearly appearing only on the top of the tablet, and it's, according to literature, it corresponds to some silicon coating. And the tablet body, it has all the peaks from all the peaks which are green color, they also present on the red spectrum because coating is highly transparent. Okay, and when we do 3D mapping, for example with fluorescence, we can also achieve 3D images. For example, here we have some network of polymer, fluorescent polymer image. And this is a multi-layer polymer film, and different position in Z, it is shown by different color, and it corresponds to different type of polymers. For example, first one is polypropylene, acrylic layer, and polyethylene tetraphthalate layer. So for some packaging production, it's very important to know the profile of such polymers, multi-polymers films. And here we can see high resolution image of test sample polystyrene microsphere, and XY of the size of this 3D image is about 10 by 10 microns, and in Z direction they are about, the image is about 15 microns. So the resolution is diffraction limited, it is 200 nanometers in XY direction and 500 nanometers in Z direction, and therefore the shape of the spheres, they looks like circles, they are not like elliptical. Okay, so when we have such a spectrometer, such a confocal microscope, of course we can use it not only for Raman, we can use it for both Raman and for example microphotoluminescence. And this is example of molybdenum disilane flakes, and there is a property of such flakes when it is a single layer molybdenum disilane flake. It has a very strong photoluminescence. When it is multi-layer structure, like shown by red color region, it has no photoluminescence at all, and double layer B layer region, it has rather weak photoluminescence. And when we choose a wide spectral range grating, we can collect both Raman signal, which is far away from photoluminescence, and photoluminescence peak, which is located at about 800 nanometers when excitation is 473 nanometer. And we can do simultaneously Raman imaging and microphotoluminescence imaging. And you can see that the Raman signal here, it shows the presence of material. Here flakes, they are present, but by photoluminescence we can identify number of layers, because by Raman it's not straightforward to understand how many layers in these selected regions. Okay, so for living cells, for some algae cells, it's possible to make fluorescence mapping of the cells, and also in addition some strong Raman peaks from these cells, which corresponds to beta carotene band. So it's possible to make such combination for the single scan. And as I mentioned, we can do in a spectrometer channel, we can put not only CCD but also some other detectors like avalanche photodiode or PMT. So in addition to Raman or fluorescence, we can do fluorescence lifetime imaging. It means when the pulsed laser excites fluorescence and decay curve is measured for each point. So photoluminescence and fluorescence signal is quite uniform in this sample. It is a mixture of two types of genetically modified Escherichia coli bacteria, and one type has produced fluorescent proteins which has shorter lifetime, and the other type of Escherichia coli bacteria, they produce proteins which has a longer lifetime of fluorescence. So blue color and orange color on this left hand side image, it corresponds to different type of genetically modified bacteria. So in living cells, the Raman signal is normally very weak, and we cannot apply strong excitation because living cells can be damaged by high intensity of the excitation laser. And to improve the intensity of the Raman signal, it is possible to use, for example, surface enhanced Raman scattering. And in this paper it was identified living cells and dead cells, and also it was monitored the apoptosis process in such living cells. So some peaks appeared when the cells are still alive, and some new peaks appeared when they dying, when the process of apoptosis is occurred. Okay, and there is also important unit in the spectrometer. It is kind of filters what we use, and here we can see Bragg volume filters. There are a lot of planes, a lot of alternative refractive index changes in the filter, and as a result such a volume Bragg grating filter, it has very narrow spectral band, and you can see comparison of Bragg volume filter, which is in the center, brown color, and comparison to the normal notch filter. So normally it allows to come close to the laser line notch filters. It's about 250, maybe 300 wave numbers, not closer. And with high quality edge filters we can get probably down to 70 wave numbers, maybe 50 wave numbers if we make a tilt of the filter. And using low wave number Bragg volume grating filters, we can get about plus minus 5 wave numbers, and therefore all the hidden lines which are not available for common filters, they become available. So this is cadmium iodide spectrum, and you can see there are two clearly resolved lines close to the laser line, and their position is about 15.8 wave numbers, and the other line at 45 is also normally hidden when we use a standard edge filters. And this is typical spectrum of sulfur. It also has a lot of peaks below 770 wave numbers, which are not available for standard filters. And again, Stokes and anti-Stokes spectroscopy allows to get additional information, which is temperature on the surface in the laser spot. Another feature of the systems is using high resolution spectral grating. So there is an Shelaev grating which works in a higher order, for example 60 order or 55 order, and it allows to resolve a peak with very high resolution, and pixel to pixel resolution is 0.1 wave number. And of course if you apply some fitting, we can get precision of peak position even about 10 times better. And it is a very important parameter, for example for semiconductor applications, when peak position is directly proportional to the stress in the material. So some oxidation of silicon inside the structure, it produces additional stress on the edges and especially on the corners. And the Raman map of peak position, it can identify stress in the structure. So here on the map the stress varies, the Raman peak position varies from 0 to about 2 wave numbers, and stress in the structure varies from unstressed to 600 megapascal. And what are the possible scanning technology we can use? So there are several ways how to make a map, how to scan by laser in respect to the sample surface. Each of them has their own advantages and disadvantages, and also they can be combined between each other. So for example, piezo scanner, bottom stage piezo scanner stage, allows to get highest spatial resolution. So it can go down to nanometer level, and it could be useful when you have to operate at a very low, at highest XY resolution, about 200 nanometers. In this case, of course, piezo scanner can show advantages in respect to motorized stage. Motorized stage allows to scan a very wide ranges, about 7 by 5 centimeters as positioning range, but the step size for motorized stage is about 100 nanometers. And also there is a galvanic mirror scanner, which allows to scan by the laser spot, and it can do it very fast, up to 3 microseconds per point. And also what's important, it is not disturbing the sample while moving it, while scanning, because some structures like fibers, these structures, they are easily disturbed when the sample stage makes scanning procedure. So here we have carbon fibers and ultra fast Raman imaging with galvanic mirror, and to get the image of the G band for such fibers, it takes about 90 seconds. Okay, let's go back a little. So the main issue in this case, when you need to make a fast mapping, is sample should produce a strong Raman signal, and in this case you can get really fast images. So up to 5 minutes for 300 by 300 pixels when you get Raman band distribution, or laser intensity distribution even with a higher amount of pixels. So this image is obtained by EMCCD scan, and let me show you how it works with fast detector with avalanche photodiode. So there is a spectrum. Okay, there is a spectrum of silicon with a grating which is low spectral resolution, but it covers wide range, and we should choose a position in nanometers. We can then put this number in wavelengths and therefore send this peak to avalanche photodiode port. So we should change in the software the output port. This is photomultiplier tube port, and after the mirror is switched, we should select scanning size and number of points, 150 by 150, and scanning speed, which is 250 Hertz. It means it makes about hundreds of lines per 1 second. Okay, and then in live mode you can see how it is possible, how fast it is possible to get Raman image of the silicon band, because on the avalanche photodiode there are signal which goes from silicon spectrum band. Okay, another position just to show how it works, and this is about few seconds to get such high resolution image, 30 by 30 microns with about 200 nanometers step. Okay, as I mentioned, we can get also information about stress. So this information is can be calculated from the Raman peak and then make a map of these structures of carbon fibers. This is example of two detectors attached to the spectrometer, and for example one of them for near infrared and the other one for visible range. And there is another sophisticated application and system. The most sophisticated system which we produce is CARS system for coherent anti-Stokes Raman scattering, and this is how it looks like. This is the excitation laser systems. It has to be several lasers combined in the system. And what is coherent anti-Stokes Raman scattering? It is a four photons mixture process, and there are photons which allows to excite the system. It's so-called pump beam. Also, in addition to pump beam, there is a Stokes photon which depopulated from this level and excite again to the highest level. And in this case, the anti-Stokes emitted light is the anti-Stokes emitted photons, they are emitted at the energy lower than excitation energies and with a very high intensity. So two beams of pump and Stokes and anti-Stokes, they should be properly aligned in terms of directions, in terms of time positioning, because normally they are pulsed lasers, and as a result the efficiency of anti-Stokes band it is improved significantly. So this is comparison of some test sample, and in spontaneous Raman the intensity for the same exposure time is about 70 counts, and with coherent anti-Stokes Raman scattering intensity is around 40 thousandths. So the difference is about 3 orders of magnitude. And it's especially important for living cells measurements, because we cannot excite them with visible range excitation lasers, and with infrared they are quite stable, and especially for living cells the fluorescence is not excited when we apply excitation in near infrared region, and anti-Stokes beam it has lower wavelengths than excited fluorescence, and it's also a big advantage for biological samples. So here we have map of different type of structures inside the cells. For example, DNA is green color, RNA is red color, proteins, lipids are gray color, and the image is obtained for selected type of the band. The overall image is just 3 seconds because intensity of the signal is quite strong. This data was obtained in the system in the United States in the University of Buffalo. And this is Raman peak of CH bond, and selective lipid visualization can be done. So bright positions on these images on the right hand side, they are the specific lipids in the cells, and the left hand side is just a transmission at excitation about 1064, and so there are some accessories for temperature control combined with Raman measurements, for example cryostat or heating stage, and it can allow also operation in controlled gas atmosphere and cooling heating stage, also with the possibility to apply voltage and detect current from the sample. So all of these accessories are available in combination with all the confocal Raman microscopes, and we hope that for most of the Raman applications we can find the proper system, and we can fit the needs of researchers by choosing the proper system for their needs. Okay, thank you for your attention.